then let's finally talk about math. So what we're going to first discuss, we're going to discuss section 10.1. And the name is section like introduction to parametric equations. Let's say parametric functions. Yeah, parametric functions. Parametric function. Okay, so here we probably need to discuss what is a parametric function. But before that, we need to remind ourselves what is like Cartesian function or what type of function we studied before. So before, we study like Cartesian functions. Cartesian functions. What is like Cartesian function? Cartesian functions, you remember, I don't know like if you heard this word before or not. It's going to be the function of the form is y is equal to f of x. So that the function which can be drawn in R2. Yes. So y is equal to f of x is going to look something like this. Y is equal to f of x. A couple of like things that we terms that we use, that x here is independent variable and y is dependent variable, because y you can see depends on x through like function f. And since like this is already like multivariable calculus, you need to be comfortable with functions of the form y is equal to e to the x or y is equal to ln of x, just to know their domain, their how the graph looks like, etc. Also, you need to be comfortable with trigonometric functions. So y is equal to sine x, and let's say y is equal to tangent x. For this one, you probably don't need to know how to graph them, but you need to understand like how to find the value of y if you know the value of x. And what else? And the standard one, let's say you need to know if the functions y is equal to x squared and y is equal to, like, for example, like 1 over x. Because all these functions, we're going to generalize them to, so first we're going to talk about parametric functions, and after that we're going to talk about multivariable functions. And when we're going to have multivariable functions, we're going to add one more variable to this function. Okay, so this is a Cartesian function, and I don't know if you, do you want me to sketch graphs or anything related to one of these functions? Do you have any questions? Yeah, I need to create next time polls so I can ask a question and then you can see your responses by answering the poll. Okay, so, but now, it's not this one. Now we're going to study something interesting. And the things that we're going to study, I need to come here now. Now we're going to study parametric functions for like first like 3 days, parametric functions. So what is a parametric function? The idea is the following, that you take y is equal to f of x. And here we have that x is independent variable. So what can we do? We can make x to be a independent variable. And the way how we're going to make x to be independent variable, we're going to introduce a new parameter. So you're going to say, so this process, this arrow is going to be introduce like t, where t is going to be a new parameter. So I'm going to say that my x is going to be equal to, let's see, let's make it like g of t. And then you can see that if x is going to be g of t, yeah, let's do it separately here, then your y is going to be depends on x. But since x depends on other function, then from here it will follow that y is going to be depend on some function, let's call it like h of t. And I'm going, don't worry, I'm going to do an example. So then y is going to be equal to some h of t. And another thing, so this is like almost a definition of the parametric functions. But another thing, like now we introduce some t. And the last component to have the definition of the parametric function, you need to tell what is going to be the bounds of t. And t is going to be you're going to change it within like some closed interval or like open interval. We're going to discuss different examples. Okay, and this information over here, like this red box, is exactly definition of parametric function. So you can see how parametric function is just when you have x in terms of x as a function of t, y as a function of t, and t changes within some interval. Let me do an example. It's a section. And based on this example, I will ask you if you have any questions. So example. So let's take, for example, x is equal to t, and y is equal to t squared, and t belongs to 0, let's say 2. So you can see that over here, you're given a parametric function because you have x in terms of t, y in terms of t squared, and t changes between 0 and 2. But then the question is like, okay, so this is like parametric function. This parametric function came from some Cartesian function. What is the graph of that function? So in other words, like what is the difference between Cartesian and parametric functions? To see the difference, let's take this parametric function right now and graph it. So what we're going to obtain. First, we're going to have our like Cartesian coordinates, which is like x and y. And do you remember like how to graph functions like since like from like when you learn like in middle school? Let's use the first approach, which going to be doing the table. So first approach, it's like table. So for that, we're going to make 3 columns, t, x, y. And you can see t changes between 0 and 2. So I'm going to plug in 0, 1, and 2. And then when t is equal to 0, then x is going to be equal to 1. And y is going to, x is going to be equal to 0, and y is going to be equal to 0. When t is going to be equal to 1, x is going to be equal to 1, and y is equal to 1 squared, which is also 1. And when t is equal to 2, x is equal to 2, and y is going to be equal to 2 squared, which is 4. So let's get these points over here. I'm going to have the first point t is equal to 0. Then I need to make x, y coordinates. So the second point is going to be t is equal to 1. And the third point is going to be, okay, I need to make y slightly longer. 3, 4 is going to be t is equal to 2 is over here. And you can see that what I'm going to have here, I'm going to have here a part of the parabola. So one feature that parametric graph has that Cartesian graph doesn't have, that right now, since I can vary my t, on this graph, I have a direction. So, and direction is going to go when I'm going to change my parameter t from the lower value to the upper value. This is going to be my direction. So, yeah, does anyone have any questions? I heard someone like that. Okay, so right now you can see what is the difference between Cartesian and parametric graph. So before, if we had parabola, we had just the graph of parabolas that looked like this. It was like y is equal to x squared. But right now, if I'm going to give you the parametric graph, which is going to be x is equal to t, y is equal to t squared, and t changes between 0 and 2. then your graph is going to look like this. But you can see that this graph is going to be on the top of the Cartesian graph like this. So on the left, you have a Cartesian graph. On the right, you have parametric graph. The feature for the parametric graph, you have initial point, you have ending point, and here you have direction. Okay. And this is basically the whole idea for section 10.1 is to introduce parametric graphs and do some examples. So we did example number 1. Let's do other example. So can you do as a practice right now, example? So let's take x is equal to t squared, y is equal to t to the 4th. And let's say t changes between -2 and 1. So can you please sketch right now the graph of this parametric function? You're going to have a couple of minutes. And then I'm going to show you the solution. Yeah, so probably the first approach that you can do, is like using the table. And we literally can repeat the same process using the table. But let me show you the second approach, which is like really important. So, and let's say like the first approach is going to be a homework problem. Let's discuss second approach. So second approach is going to be called like eliminating the parameter. So do you see like how we defined parametric function over here? We took the Cartesian function and we introduced a new parameter t. So eliminating parameter means we're going to do opposite. So here we have x is equal to t squared and y is equal to t to the 4th. So we're going to sketch that graph by figuring out first, so step number 1, kind of finding Cartesian graph. So how are we going to do this? You can see that x is equal to t squared and y is equal to t to the 4th, which is t squared. So that means if I'm going to replace t squared with x over here, you can see that I will obtain the graph y is equal to x squared. And we know what is the graph of y is equal to x squared. It's going to be just equal to this parabola over here. This y is equal to x squared. But if you're going to write that as your final answer, that's going to be wrong, because you can see that for parametric graph, we have really important like variable t. So we know that when t is equal to -2, we're going to have our initial point. And when t is equal to -2, I will have that x is equal to 4. And y is going to be equal to, let's see, 16. And then when t is going to be equal to 1, we will have x is equal to 1 and y is equal to 1. So when I have 4 and 14, I'm going to have point over here. So it's going to be 1, 2, 3, 4. So that is going to be a point. T is equal to -2. And then you can see, then we can imagine this like this. So this is -2, this is 1. And let's say this is going to be 0. So t parameter is going to track that interval. So when t is going to go from -2 to 0, Can anyone tell me, is your point is going to move up or move down?
It'll move down.
Move down, yes. So when t changes from -2 to 0, we're going to move to the origin. So we see this is t is equal to 0. Can anyone tell me what is going to happen when t changes from 0 to 1? It's going to move up or down?
Up.
Up, yeah. So we're going to go from this point t is equal to 0. I'm going to use, let's say, like a red one, to this point 1, 1. This t is equal to 1. So the seal is then your whole path of your particle is going to be kind of this curvy path. You first reach the origin and then you move slightly back. So based on this example, can anyone tell me what is like unique about parametric graph? What we can do with parametric graphs that we can?
Right.
Yeah. So using parametric equations or like this, like parameterizations, in other words, we can make our like particle in the graphs move like really using like really interesting trajectories. So, sorry, what?
These are called vectors, right? Or like it's more like they have a direction type-ish.
Yeah. So direction is this. It looks like this when t changes from -2 to 0, and then from 0 to 1 is like this. So you just draw the arrow. We're going to talk about vectors later, like probably this week. Yeah. But right now you need to know when you sketch the parametric graph, you need to have indicate your initial point, your ending point, and show direction, of course. So probably let's do a couple of more practice problems. Okay, so I don't want to move. Let's see. Okay, let's do another example. Okay, and for this example, what I want to do, I want to, let's say, take x is equal to t, and y is equal to 1 over t. And let's make t changes between negative infinity and positive infinity. So what we're going to get over here. So first, recognize that, do we want to do a table here? Like, no, because we have infinitely many values, and like just, if you see a nice function, nice parametric function, you need to always try to use the second approach over here. So you see there's like some questions. Yeah. And second approach is just eliminating the parameter. So that means if you're going to eliminate the parameter, then my y is going to be just equal to 1 over x, yes? And we know what is the graph of that function. It's going to be hyperbola. So you need to be comfortable sketching the graph. When x is equal to 1, then my y is going to be 1. So I have point over here. When x is going to get smaller and smaller and smaller, my value of y is going to get bigger, bigger, and bigger. So for example, if x is 1/2, then y is going to be equal to 2. So you can see that your graph is going to look something like this. And then we're going to also have the second part of hyperbola. So right now we have 2 parts of hyperbola, like part 1 and part 2. Can anyone tell me what is going to be the graph of that parametric equation in this Cartesian coordinates? Yeah, we have like branch 1 and branch 2. So it's going to be branch 1, branch 2, both of them. Yeah, to figure that out, let me show you how to figure that out. So when t is going to be equal to -1, yes, then what is going to be my x? My x is going to be equal to -1, and y is equal to -1. So when x and y is equal to -1, I'm going to get point over here. It's going to be t is equal to -1. And then let's do the same what we did before. If right now I'm going to think about my interval as from -infinity to +infinity, and this is like t is equal to -1. Then if I'm going to change my t between -infinity to -1, what happened with this point? When t is equal, for example, to -10, you're going to have point over here, yes? If it's like -10, it's going to be -1 over 10. So when t changes from between negative infinity to 1, you're going to have this part of the parabola. But here, can anyone tell me what is constraint should I make for my interval? Is there like some sort of mistake? Is it possible to have t negative?
0, right?
Yeah, I need to exclude 0. So that's why I need to change my t from negative infinity to 0, union 0 to positive infinity. And you can see that if you're going to take the first interval, the t changes between negative infinity and 0, you're going to get the second branch over here. So this is branch when t changes between negative infinity and 0. And if I'm going to make my t changes between 0 and positive infinity, I'm going to have this branch from 0 to positive infinity. Okay, so I indicate these arrows as I know my direction. Since I know when t changes from smaller value to the bigger value, it's where my particle is going to go. Can you tell me what is going to be your initial point? Do we have some value of t for which you can say, like, for this value of t, this is going to be point on my graph?
Not for an initial point.
Yeah, there is no initial point, and there is no ending point. So you can see sometimes your parametric graph can miss some of the pieces of information. So usually when your teaching is between like negative infinity to positive infinity minus some points, then you might have no initial, no ending point. Okay, so I did like a couple of examples, like 3 examples of parametric graphs. Right now is like we can either move on, discuss some other stuff. Do people want to see more examples? And can you ask me some questions? Which part is confusing about this parametric graph so far?
Well, you said to use that second approach first when we do problems, right?
Mm-hmm.
Okay, just making sure.
Yeah. So for example, let's do, I will give you some time to think about it. Let's do the following graph. So I'm going to take x is equal to cosine t. This is going to be like, this is probably the most important example in this class. Y is equal to sine t, and t changes between 0 and pi. What I want to do, yeah, for example, this example is what you're going to expect to do in homework. We have cosine t, y sine t, and t changes between 0 and pi. So let's find the parametric graph of this parametric equation. So for that, I'm going to use a second approach, which is like eliminating the parameter, second approach. So we can see that we have x is equal to cosine t and y is equal to sine t. So can anyone tell me what can we do to get rid of t? Do you have any ideas? Yeah, we need to use a trig identity. We know that we have cosine squared t plus sine squared t is equal to 1. Yes? It's probably the main trig identities that you need to know. So from here then follow, if you're going to take your equations and square them, you will have x squared is equal to cosine squared t. Y squared is going to be equal to sine squared t. And then we're going to add x squared plus y squared. I'm going to have x squared is equal to cosine squared t plus y squared is equal to sine squared t. And they're equal to 1 since we use this trig identity over here. So in other words, my Cartesian equation of that parametric equation is going to be x squared plus y squared is equal to 1. Can anyone tell me what is the graph of this Cartesian equation?
Circle?
Yeah, circle. So here, I'm not going to sketch the whole, like the solid circle. I'm going to sketch dash circle. Can anyone tell me why?
Because we are only going to take part of the Cartesian function graph.
Yeah, because we have this restriction over here. So can anyone tell me what is going to be your initial point? Yeah, it's going to be 1, 0. And the way how we figure this out, because initial point is going to be your first value of t. So for your first value of t, when t is equal to 0, you will have x is equal to cosine 0, but cosine 0 is 1, and y is sine 0 is 0. And can anyone tell me what is your ending point? You will see that, actually, I'll just answer. X is going to be equal to -1, and y is going to be equal to 0. So in this graph, we're going to have that this is my ending and initial point, and this is my ending point. But right now we have a problem. We can go either this direction, yes, or this direction. So which path do we choose, top or the bottom? Yeah. Or in other words, we can do a test point, t is equal to pi over 2, and t is equal to pi over 2 will give me cosine of pi over 2, which is 0, yes. And y is equal to sine of pi over 2, which is 1. So that's why I know that when t is equal to pi over 2, I'm going to go through this point. So as soon as we have initial point, ending point, and we know which branch of the graph we need to choose, I'm going to sketch my graph. And don't forget, indicate the direction by that arrow. Okay. So right now at this point, I think like you just need to practice doing and sketching the graphs on your own. So let me just summarize. The first approach that we did, you can just sketch a table just to get used to parametric equations. And remember, pay attention, like what is your boundaries for t. So your first value of t is going to be initial point, last value of t is your ending point. And then when you're going to sketch your graph, don't forget to indicate the direction. Then we learned that we have, we can get, do you see like one like important example that here we have a parabola, yes? And here we also have a parabola. But for this parabola, we have a different parameterization. And that parameterization gave us this interesting trajectory. So, and how we sketch that graph, we didn't use a table. We used the eliminating the parameter. So the idea is like to get rid of parameter t using either algebra or something like trig identities. And after that, when we know approximately how our graph looks like, we start plugging in points and analyzing if we're going to like change our t, how like the movement of the particle is going to, how the particle is going to change. So where the particle is going to go. So here you see if t when changes from -2 to 0, we will approaching the origin, and then we move slightly up when t was changes between 0 and 1. So the idea here is like different parameterizations will give you different trajectories on your graph. Okay. So before I'm going to move on, do you have any questions about section 10.1? And in this section, what we're going to do right now, we're going to do calculus with parametric equations. So you remember that we learned a lot of different concepts, like taking derivatives, finding the equations, the tangent lines, etc. And what do you want to do right now? We want to generalize those concepts to parametric equations. So first, we have our Cartesian equations, y is equal to f of x, versus the parametric equation, x is equal to g of t, and y is equal to h of t. And t changes between like a and b. The first concept is taking derivative. So the first one is taking derivative. We remember that when we talk about the derivative of my function, I can indicate this as y prime, but at the same time is going to be equal to f prime, yes? But also that is going to be notation dy over dx. Because as you remember, the meaning of derivative, if you have some function y is equal to f of x, let's sketch it like this. And I will ask, okay, so I want to find f prime of point, like for example, like at 0. Then that means you're going to choose point x is equal to 0, and this point f prime is going to tell you about the slope at that point. Just small revisit what is the meaning of derivative. So it's just slope. It gives you the value of the slope at a certain point. But how do we find right now? So for example, if you have y is equal to x squared, y is equal to x squared, then derivative of your function is going to be just 2x. Okay. But how do we find, for example, derivative of the function if your function is given in terms of parametric equations over here? So the idea is the following. Let's write down derivative using this notation. So I'm going to have dy over dx. And do you see, like here, I took the derivative where y is my function and x is my independent variable. So since here right now I have y and x as a function of some variable t, so what can I do? I can treat dy and dx as like variables, like as a fraction. So and then I can do a trick. I can just divide both top and the bottom by dt. So we'll have dy over dt, and then I will have dx over dt. So in other words, I will have y prime of t divided by x prime of t. Or in other words, I'm going to have g prime of t divided by x prime, h prime of t. So if you want to find the derivative of your parametric equation, again, like all red boxes are going to be the formulas that you need to know. You need to use this formula over here. So let's do an example. Let's take the same function over here, y is equal to x squared, but I'm going to take its parametric form. So can anyone tell me, give me the parameterization of the parabola, for example? Then what is your x and what is your y?
But I have a question.
Yeah.
Is it g prime over h prime or h prime over g prime?
Oh, sorry. Yeah, thank you. It's h prime. Yeah. H prime over, it's y prime, h prime over g prime. Yeah. Can anyone give me a parameterization for x? Or also that works with the like t squared and t to the fourth, yes? Because if x is equal to t squared, then y must be equal to t to the fourth. Okay, let's find the derivative then. And let's do, okay, so we have dy over dx. Then we can see that my x prime is going to be equal to 2t. My y prime is going to be equal to 4t cubed. So if I'm going to plug in them over here, I will have 4t cubed over 2t is going to be equal to 4 and 2 got canceled, so 2, and t and cube gonna get canceled, so 2t squared. So dy over dx is going to be equal to 2t squared. Okay, and you can see that here you have x squared is equal to t squared. Yes. So if you're going to replace this t squared with x, you exactly is going to get your Cartesian derivative. Can you do x is equal to t plus t cube and y is equal to t minus t cube? And can you find the derivative when t is equal to 1? Okay, I'm back here. So to find the derivative, I need to find just dy over dx. So that is going to be equal to y prime over x prime. But we can see that my x prime is going to be equal to 1 plus 3t squared. And then y prime is going to be equal to, oh, it's, yeah, 1 minus 3 t squared. So then my derivative is going to be equal to 1 minus 3t squared over 1 plus 3t squared. And since I want to find derivative at some specific point t is equal to 1, then what do I need to do? I just need to take the notations that we're going to use is dy over dx when t is equal to 1. is going to be equal to 1 minus 3 times 1 squared over 1 plus 3 times 1 squared. So it's going to be equal to what? It's going to be equal to negative 2 over 4. So it's going to be equal to negative 1/2. So dy over dx is going to be equal to negative 1/2. Okay. So basically, it's a summary, like to find derivative of the parametric function, you need to find the derivative of each separate x and y component separately, take their ratio, and if you need to find some specific value, just plug it in that value inside your parametric equation. Okay. And again, like what we're going to do today, I'm just showing you basic examples. I'm going to give you the worksheet, and then we're going to do a lot of practice problems tomorrow. Okay, so this was the first, taking derivative, and then second idea is finding tangent lines. Finding tangent lines. Okay, so if we have function y is equal to f of x, and let's say you want to find the derivative, the equation of the tangent line when x is equal to x naught, then for that, what do? We just need to find the all unknowns in this equation, and the equation is the following: is y minus y naught is equal to f prime of x naught, x minus x naught. So my unknowns over here are going to be the following: is y naught and f prime of x naught. Can anyone tell me what do you need to do to find y naught? Y naught is actually when I'm going, instead of x, plug in f of x naught. So it's just value at that point. So it's going to be f of x naught. For f prime of x naught, you just take the derivative and evaluate the derivative at that point. So, and right now what we're going to do, we're going to take this equation and just rewrite this equation using our parametric like parametric form. So what I'm going to do, we have the parametric equation x is equal to g of t, y is equal to h of t, and right now you can see if before we had our like parameter x, here our parameter is t, so I'm going to have t is equal to t now. And then the equation I just going to rewrite is going to be y minus, and what do I have over here? I have h at t naught is equal to derivative of my function, yes? But derivative I'm going to indicate as dy over dx when t is equal to t naught. And then I'm going to have x minus x naught, but x minus x naught is going to be just x. I need to use blue one. So I'm going to have x minus x naught over here is going to be what? Is going to be g of t naught. G of t naught. Okay. And here's also this unknown. Okay, and this is going to be our second formula that you need to like remember. So basically, I didn't introduce anything new. I just rewrote the previous equation of the tangent line in terms of parametric equation. So let's do this as a practice. Let's do some practice problem. Okay. So for practice problem, let's do the following example. Let's take x is equal to cosine t, y is equal to sine t, and I want you to find the equation of the tangent line when t is equal to pi over 4. So first, I'm going to rewrite this equation in the following form as y minus y naught is equal to, it's not f prime, dy over dx t at pi over 4. Oh, sorry, this is not like y at naught, this is y at pi over 4. Times x minus x at pi over 4. So this x at pi over 4, it means just I need to evaluate my y value at pi over 4. So what I'm going to get in this case. To do that, we can see that x at pi over 4 and y at pi over 4 are going to be equal to cosine of pi over 4, which is square root of 2 over 2. And sine of pi over 4 is going to be equal to the same value, square root of 2 over 2. And then by knowing these two values, we already figure out the first component and second unknown component. So the only thing which is left is to find the derivative of the parametric function. But to find the derivative, what do we need to do? I have just dy over dx. So that's equal to y prime of t divided by x prime of t. So I'm going to have cosine t over sine t. Yeah, and then if I'm going to plug in t is equal to pi over 4, that's what I'm going to get. I'm going to get square root of 2 over 2 divided by square root of 2 over 2. So I'm just plugging t is equal to pi over 4. And then square root of 2, they're going to cancel out, so I'm going to have 1, yeah? Okay, and so to finish this problem, what I'm going to have? I'm going to have y minus square root of 2 over 2 is equal to 1 times x minus square root of 2 over 2. And that's going to be the equation of the tangent line. So basically, you can see the finding the tangent lines is similar to calculus 1, where we have just one extra step, finding the value of my y in terms of t. Okay, but sometimes these problems might be tricky, and you're not going to be given your t right away. Let me show you an example. So instead of, you can be just asked to do the following example. You can be given a parametric equation. Let's say x is equal to t squared and y is equal to, actually, let's take 2t. X is equal to 2t and y is equal to 4t squared. And then you can be given like a point, 2 and 4. And you will ask to find the equation of the tangent line, this point 2 and 4. And this point 2 is 4 is your x and y, yes? So you don't give in like your parameter t. So the trick is, first, as a step, you need to figure out what is your t. And to figure that out, I know that x in terms of t for some t is going to be equal to 2. And y in terms of t is going to be equal to 4. Because remember, like to find the equation of the parametric equation, we need to know our value for t. And for that, I know that x of t from here is equal to 2t. So I have going to 2t is equal to 2. And y of t is going to be equal to 4t squared is equal to 4. So if I'm going to solve the system by dividing first equation by 2, I'm going to have t is equal to 1. Oh yeah, I did a mistake there. Oh, sorry about that. It's x is equal to minus, yeah. Minus. Thank you about that. Yeah, sometimes I might do like small arithmetic mistakes, so please catch that. Okay, so it's going to be -1. Thank you. Then t is going to be equal to 1. and t squared is going to be equal to 1. So if you're going to solve the system, you will see that we're going to have t is equal to 1 and t is equal to plus minus 1. But you need to choose a parameter t, which is going to be the solution for the first equation and solution for the second equation. And from there, you can see the only solution which the same is t is equal to 1. So right now we have the setup for finding the tangent, the equation of the tangent line. I have x is equal to 2t, y is equal to 4t squared, and t is equal to 1. So, and then I can find the equation. So I'll have y minus the value of y at 1, which is going to be 4, is equal to the value of its derivative, that I'm going to find in a second, times x minus the value of my x when t is equal to 1. So it's going to be 2. So, and my derivative of dy over dx is going to be equal to y prime over x prime. So it's going to be equal to 8t over 2. So it's going to be 4t. And then I need to plug in when t is equal to 1. So when t is equal to 1, I'm going to get 4. So I will put 4 over here. And that is going to be the answer for the equation of the tangent line. Okay, so this was like 2 examples for finding the equation of the tangent line. So sometimes you can be given your parameter t, and sometimes you don't know what is your t. So you need to do like this step to figure out what is your t. So it's like one tricky thing. Okay, let's do the next example. So the third one is finding area. Finding area. And we know that if we have y is equal to f of x, and I'm going to restrict my x to some closed interval, x between a and b. You can visualize that we have the graph that looks something like this. So we're going to have this graph, y is equal to f of x. Then if I want to find the area below the graph between like a and b, then what do I need to do? I need to compute the definite integral between a and b, so let's call it area a, of f of x dx. Yes, but my f of x is equal to y. So I'm going to replace my f of x as y. I'm going to have the integral between a and b of y dx. And right now, the idea to find the area for parametric equation, I just need to take this integral and rewrite that integral using parametric equation. So for that, remember that your parametric equation is given by x as x of t, not x of t. It's also equal to x of t, but I said like before, it's g of t. Y is equal to h of t. And let's say you can see that when your x changes between a and b, then for this point over here is going to be some t naught, such that the t naught is going to be given the function, that is going to give you the point g of t naught and h of t naught. And for this, we're going to have some t1, such that that point is going to be g of t1 and h of t1. So in other words, every Cartesian point on the graph in Cartesian coordinates corresponds to a single value of t. If you're going to plug in the t, you're going to find your x component, your y component. And since t1 is bigger than t naught, I'm going to have like that direction over here. And then I have the t changes between t naught and t1. So what I want to do, I want to take this integral over here and just rewrite this integral using my parametric equation. So not f of x, I want to use y. Y is equal to dx. Okay, so first you can see that if I have function y, then my function y is going to get unchanged. I'm going to have just h of t. So that's why over here I'm going to have integral of h of t. But then I have my second term. My second term is dx. So what do you do with dx? This is like illegal, but we have that dx over dt, yes, which is my g prime of t. So you can see that if you will think about left-hand side as a fraction, then what you can do, you can multiply both sides by dt. So, and then what we're going to obtain? We're going to obtain that dx is going to be equal to g prime of t dt. So that's why that dx over here is going to be replaced with g prime of t and dt. And the idea of the integral that dx dictates what is going to be bounds, what is variable you're going to use to compute your definite integral. And here I have that my x is bound between a and b. So that's why I have my bounds is a and b. But this integral, you're going to integrate this those functions corresponding to t. So that's why like the bounds of your integral are going to be the bounds for t, which is t naught and t1. Okay. And this formula over here, let me rewrite it. Sorry. That area for parametric graph is going to be integral between t naught and t1 of h of t, g prime of t. Let's try this one. So let's take x is equal to cosine t, y is equal to sine t, and let's say t changes between 0 and pi. So for all these problems, what I strongly recommend this multivariable calculus class. It's really important to be able to visualize. And a lot of concepts you can understand if you're going to see what is going on. So first, for example, I gave you some parametric equation. And the first question you need to like ask yourself, okay, what is the graph of this parametric equation? And we already did that. So I'm going to revisit the same problems. Is going to be a like upper circle. So it's going to be this graph over here. And this is like when t is equal to 0, t is equal to pi, and that's my direction. Yeah. So when I want to find the area, I'm going to find the area of this region. So of this area. Yeah. So let's compute this. So finding the area is going to be computing the integral between 0 and pi of derivative of my sine function. Because remember, what do we have? We have that h of t is equal to sine t, and g of t is equal to cosine t. Yeah. And if I'm going to use a formula over here, then I need to plug in h of t. Then I know that my g prime of t is equal to negative sine t. So I'm going to have negative sine t. And then dt. Okay. So after this, what is the integral is going to be? I'm going to have integral between 0 and pi of minus sine squared t dt. I'm going to have minus. Does anyone remember how to find the integral of sine squared t? So what do I need to do?
I think you have to use double angle formula.
Yeah, there's one
Or
formula
half
you need to
angle.
remember. Yeah, half angle formula that sine squared t is going to be equal to. So the way how it goes, I remember it's 1, 2, and cosine 2t. So the only thing that we need to figure out is it going to be plus or minus. So do people remember? Do I need to put plus or minus there? So then what I'm going to obtain, I will have 1 minus cosine 2t divided by 2 dt. So that is equal to minus integral between 0 and pi. And I'm going to split this fraction. I'm going to have 1/2 minus 1/2 cosine 2t dt. And then since I have the integral of the difference of two functions, I'm going to split this integral. So I'm going to have minus integral between 0 and pi of 1/2 dt minus 1/2. I'm just going to pull the constant from the integral of cosine of 2t dt. Okay. So if I'm going to distribute the minus sign, I'm going to obtain minus 1/2 integral between 0 and pi dt. And here I'm going to have a plus 1/2 integral between 0 and pi cosine of 2t dt. Let's see the chat. So the value of the first integral is going to be equal to negative pi over 2. But the second integral, you can compute it, you can tell me the answer even without computing the integral. Do people see what is going to be the value for the second integral?
It's going to be minus pi.
Minus pi, I think it's actually going to be 0. And the way how to see this, let me show you like the trick. If you're going to integrate cosine of 2t, yes, you're going to have like some constant times sine of 2t. But sine of 2t is going to be between 0 and pi. But sine at 2 pi is 0 when I'm going to plug in t. And when sine at 0 is also going to be 0. So that's why this term over there is going to be 0. But if I'm not going to cheat and I'm going to actually compute this integral, then let me do it over here. So what I want to do, I want to compute the integral of 1/2 of from 0 to pi of cosine of 2t dt. And here I'm going to use a reverse chain rule. So first I'm going to have my constant times. I will have sine of 2t. But since you have 2 over here, then reverse chain rule, I need to take the coefficient in front of t and divide by it. So I'm going to have 1 over 2. And my bound between 0 and pi. And why is it true? Because the idea of integration, as you remember, that if I'm going to take my answer and differentiate, I must to obtain my original function over here. If I wouldn't have that 1/2, so let's take a look. I will going to have 1/4 sine of 2t. If I'm going to take derivative, I'm going to have 1/4 cosine of 2t times 2. So it equals to 1/2 cosine of 2t. And that is exactly the function over here. If I wouldn't have 1/2 over here, then my final answer will be just cosine of 2t. So that's kind of, you can use as a mnemon to remember. I call this like just reverse chain rule. Okay. And if I'm going to finish computation, I'm going to have 1/4 of sine at 2 pi minus sine at 0. Because what I did, I just literally plugged in t inside. But sine of 2 pi is going to be equal to 0 and sine of 0 is 0. So that is going to be equal to 0. So that's why the answer over here is just 0. This was about finding the area. And then let's do the fourth one. It's going to be arc length. Okay, so finding the formula for the arc length, it's like I will just give you, it's L when x changes between like x naught, not x naught, let's choose a and b, and this is going to be the square root of 1 plus f prime of x squared dx. Okay, so again, like just to short review, if we have a function between a and b that looks like this, it's y is equal to f of x. Then finding the arc length, you're just finding the length of this like curved line segment. This is kind of L. So to find the arc length using parametric equations, we just need to take this formula again and just rewrite it using parametric equation notion. So here, let's take the inside of my integral. So the inside of my integral is going to be equal to the square root of 1 plus f prime of x squared dx. And just follow me and see what I'm going to do. So first I'm going to replace f prime with dy over dx. So I'm going to have 1 plus dy over dx squared dx. The next step I'm going to bring, so again, like I will treat dy dx as a fraction. I'm just doing this to save time because we don't have a lot of time to talk about like to talk into like in details, but I'm going to take this dx and bring it inside my square root. So what I'm going to obtain? I'm going to obtain 1 plus dy over dx squared times dx squared. So you see, like I just bring dx inside the square root. And then what I can do, I'm going to expand that fraction. So if I'm going to expand that fraction, what I'm going to obtain? I'm going to obtain dx squared plus dy squared. Okay, I hope that you don't have any questions. Then remember that we have x is equal to g of t and y is equal to h of t. And then we did a computation over here that if x is equal to g of t, then dx is going to be equal g prime of t dt. So that's why I will have that dx is equal to g prime of t dt, and dy is equal to h prime of t dt. And what I'm going to do, I'm going to replace my dx and dy with those values. So I'm going to obtain the square root of g prime of t dt squared plus h prime of t dt squared. And you can see that dt squared is going to be the common factor. So what I can do, I can factor out of the square root dt squared. So I'm going to obtain g prime squared plus h prime squared dt. So we started with this expression, and using parametric equation, we ended up with that expression. So that means that what I can do, I can just take my integral right now. Let me do the next page, which is L is equal to integral between a and b of square root 1 plus f prime of x squared dx. And that is going to be the integral of g prime of t squared plus h prime of t squared dt. And remember, like, what is going to be our t-bounds? T-bounds is going to be the value for t for which, if you're going to have t naught, then that is going to give me, why it disappears? Then it's going to give me this point over here. And if I'm going to have t1, that is going to give me this point over there. So that's why I'm going to have my bounds between T0 and T1. Okay. So finally, the equation for the finding the arc length is going to be integral between T0 and T1 of G prime of T squared plus H prime of T squared dt. But since we know that G prime and H prime is going to be just X prime and Y prime, we can write this in a short notation as integral between T0 and T1 of square root of X prime squared plus Y prime squared dt. Okay, and this is the formula. Okay, so we left like 3 minutes. I just don't want to rush to do an example. Here's just example is going to be just a straightforward computation. You're going to have X and Y. We're going to do practice problems tomorrow. And you just need to plug in the formula and find your length. So let's kind of summarize what we learned today. We have 12 pages. So first, we got introduced to a new concept, which is like parametric equation. And parametric equation is the equation of this form. When you have X in terms of some, when we have X in terms of some function, then we have Y in terms of some function, and they depend on the new parameter T when T changes between like certain values. So the difference between Cartesian and parametric, that for parametric equation, right now we have initial point. Why am I jumping there? Sorry. Now we have like initial point over here. We have ending point. And also we have a direction. The first approach to sketch the graph just using the table. I recommend you to do a couple of problems just to practice. But then we can use the second approach, which is going to be the eliminator of the parameter. You can either use algebra or like the trig identity, which we did over here. Let's see. So, and this picture over here just show you a clear difference between Cartesian and parametric equation. So Cartesian equation is going to be the solid graph. Parametric equation, you have two important points and a direction. Okay. And then we did some examples with different parametric equations. And after that, we started doing calculus. And the idea of the calculus, you literally just take the formulas that we know from calculus 1 and calculus 2. Then we use the expression x is g of t and y is h of t. And we rewrite all our formulas using parametric equation notation. So, and we cover like three subsections, which is like taking derivative, finding tangent lines, which the formula over here that you need to remember. And finding the area over here. And finally, the arc length. Yeah.